In this video, we are going to look at another practice problem number 2 on the subject of charging and discharging capacitors. Number 2 reads, a circuit is used to charge a previously uncharged capacitor. The supply has an EMF of 12 volts and negligible internal resistance. It's in series with a resistance R. The graph shows how the potential difference across the capacitor varies with time after the switch is closed. So imagine that this switch is becoming closed in the circuit, and as that happens, our voltage is built up, we are charging. The first question that we're asked here is to determine the time taken for the potential difference across the capacitor to reach half of its maximum value. So I'm going to come up to my graph that shows the potential difference or voltage versus, it got cut off here, the x-axis should say time in seconds. And let's take a closer look at what that maximum voltage actually is. That'll be right here. So bringing that over, it looks like it's a little bit more than 10 volts here for my maximum voltage. So I want half of the maximum voltage. I want something that's a little bit more than 5, and that'll represent half of my maximum voltage. To determine the time at which that's happening, I'll bring that over to my line and drop that line down. And I'm trying to now determine the time at which that happens, the x value. I know that if I were to split that evenly, that would be 75 seconds. So I guess my best estimate is about 65 seconds for half of that maximum value. Next up in part 2, we're asked to calculate R, the resistance. Now the equation that comes to mind is one right out of the data booklet, this guy right here. The reason this equation came to my mind is because we're given a voltage time graph, and in this equation I see time and I see voltage. But I don't yet see R resistance in this equation because it's hidden right here in my tau. My tau is equal to RC, that's our time constant. So I'll substitute that in. Okay. Now I'm going to use my previous answer of 65 seconds to help me out here, knowing that 65 seconds represented when I halved my maximum voltage. So I'm going to plug in half V0. I'll plug in my 65 seconds. And while I'm at it, I'll also plug in my capacitance, which in this problem is given as 200 microfarads. Now, this equation is solvable. I'm noticing that V0s will cancel on either side, which leaves me with an equation that is either all numbers, but with just one unknown. To get rid of that e to the hot mess right there, we're going to take the natural log of both sides. The natural log is our way of canceling out that e, which means that on our left side, we're left with natural log of 1/2, but on our right side, we're left with negative 65 over R times 200 times 10 to the negative 6th. I'm going to multiply that R up to the other side, and I'll divide by natural log. Now at this point, if you're a little concerned, you're thinking, when we solve this, we're going to get a negative value for R. Well, I like how you're thinking, but really this natural log in here has a hidden negative. The natural log of 1/2 we could write as being the natural log of 2 to the negative 1. And a rule from math class is when you have an exponent inside of a natural log, you can actually bring that exponent out in front. So that's how we're going to deal with that negative on the top, is going to cancel with the negative on the bottom. Now plugging that into my calculator, come right over here because I ran out of room. Plugging that into my calculator, I get a big old number. Or to write it more simply, I'll do a little bit of rounding and I'll call it kiloohms for my resistance. So I've now determined the resistance as 470 kiloohms. The last part of this problem is asking us to calculate the initial charging current. Again, I'm going to use my previous answer to help me out here, thinking that R equals V over I. We are looking for that initial charging current, so we are going to use the initial voltage, or also known as our maximum voltage. So I'll take that 470K, our maximum voltage in this circuit being 12 volts, as we can see right here for our battery. And dividing that by I naught, which is what I'm trying to solve for. As you type this into your calculator, you get about 2.6 times 10 to the negative 5th amps, which we could also write as 26 microamps of current. So overall in this problem, we were able to use the graph to determine when we reached half of our maximum voltage. Then we used that time in part 2 in order to solve for R. And then finally in part 3, we used R in order to solve for the initial charging current.